A few bookkeeping items before we start today's webinar. First of all, I would like to let you know that a recording of today's webinar will be sent to everybody who has registered for today's webinar. Second, I would have a small Q&A session at the end of today's webinar. So if you have any questions for us, please feel free to type in the question in the chat window. My colleague and myself, we will be monitoring the chat window, and you can type in your questions and I'll try my best to answer them at the end of today's session. And again, for people who have just joined in, welcome and good afternoon. And we will be starting today's webinar titled Coupling to Circuits Inside EMS for SOLIDWORKS. Let us take a look at the agenda for today. First, we will start with what is this coupling to circuits and how is it implemented in EMS for SOLIDWORKS. Next, we will dive right into the program where I will be showing you an example where I've used coupling to circuit for a real-life wireless charging example. Then we will look into the workflow that one has to adopt to enable a coupling to circuit simulation in EMS. Finally, we'll take a look at the various EMS bundles and applications that the program can solve. And last but not the least, as I mentioned earlier, we'll have a very short Q&A session, and I encourage you to type in your questions in the chat window, and at the end of the session, I'll try to answer to the best of my ability as many questions as possible. Again, this particular webinar will be recorded and a copy of the recording will be sent to you. So you may share this recording with your colleagues as well. Now let us look at coupling to circuits inside EMS. Now, coupling to circuits was a new module implemented in EMS 2018. In 2018 version, this coupling to circuit feature was available only for the AC magnetic simulation. In the upcoming 2019 EMS release, coupling to circuits will be expanded to include transient magnetic study as well. As you will shortly see in the demonstration that I will show you, EMS has incorporated a very easy to use circuit editor right inside SOLIDWORKS. It has all basic components of a circuit like resistances, inductances, capacitances, etc. And it also has various sources in the form of voltage source, current source, etc. So it enables users to do multiple applications using circuit editors. For example, a transformer can be coupled to a circuit to study its behavior for various loading conditions. And the example that we will be showing today is that of a wireless charging system where circuits are used to drive the coils, and also the receiver coil has some kind of a load attached to it. Finally, circuit editing capability is not available yet with parameterization feature in EMS. Now, let me briefly take you through the demonstration example that we will be seeing shortly. As you can see in the image shown, we have two coils that form a wireless charging system. And the objective of this particular demonstration is to illustrate how one can couple electromagnetic simulation in EMS to a circuit. Next, we will use the simulation and the circuit to determine the various circuit parameters in this particular study. For example, we will calculate the flux linkage, the inductance, the resistances, etc. Then we will also be able to compute the current flowing through the receiver coil, especially through the load in the receiver coil. Finally, we will be able to determine the coupling coefficient for this particular system. And we can make a study of how the coupling coefficient varies as the distance between the coils vary. Before I jump into SOLIDWORKS, let me just briefly walk you through the workflow that one needs to adopt to enable circuit simulation inside EMS. And I'll be going over this workflow at the end of this demonstration as well. So the first step is really to create your model in SOLIDWORKS, which is a 3D CAD software that you may be familiar with. Then EMS, which is an add-in product to SOLIDWORKS. It is actually a gold certified add-in product, and it is the only electromagnetic simulation software available for SOLIDWORKS customers, which is embedded right inside SOLIDWORKS. You create what is called an AC magnetic study in EMS. And then we will couple that to a circuit. While creating an AC magnetic study, one needs to input the frequency, and we will do that. Then we will create coils and then windings, and then we will use the circuit editor to actually assemble the circuit using the windings created in EMS. Once the problem has been defined, we can run the simulation and visualize the results. Now, with this workflow in mind, let me just quickly go to my SOLIDWORKS where I have the model that I'm talking about shown. I will just wait for a few seconds so that the audience view is refreshed so that they can see the example in SOLIDWORKS. Now, if you follow the workflow I just explained to you, we use SOLIDWORKS 3D CAD to create the 3D geometry. Now that is done through creating an assembly of several parts. For example, we have a transmitter coil and we also have a receiver coil. We also have the ferrite base for both the transmitter and the receiver coil. And we are going to use this particular example to study how wireless charging is accomplished between the two coils. I can go ahead and turn on the transparency in SOLIDWORKS so that we can see the coils clearly. Now, EMS is a gold certified add-in product to SOLIDWORKS, which means that once I install EMS, I can do the electromagnetic simulation right inside the SOLIDWORKS environment. EMS has a very intuitive workflow where the first step in creating a simulation is to create a study. Now, to create a study, you can right click and create a study. EMS has several different study types, both in the domain of magnetic as well as electric simulation. For today's demonstration and for the topic for today, we will keep to a particular study type, which is called AC magnetic. Now, you would use an AC magnetic study type only if you have AC signals, which is the case in this wireless transmitter example. Once you select AC magnetic simulation, you can select the frequency. In this particular example, we use 20,000 Hertz or 20 kilohertz frequency. AC magnetic study can be coupled to several different types of simulation to enable multiphysics. In this particular example, we're going to couple this to a circuit. Once a study is created, it creates what is called as a study tree, as shown here. Inside a study tree, we march from top to bottom, and the steps are very linear and easy to follow. First, we have to define the materials for the various parts in your assembly. And that can be accomplished by right click and say apply materials. EMS comes with its own material library where we have a plethora of materials which are categorized. For example, we have conductor materials, we have steels which have their own properties such as BH curves and conductivity. We also have other categories as mentioned here. For this particular example, I'm going to use the plates are made of aluminum, and I apply the material aluminum. The ferrite obviously is made of some form of a ferrite material or iron. We use that from the material library. And the coils are made of copper. They're basically wound coils where strands of copper are wound in a bobbin to create the coil. For every electromagnetic simulation, one needs to define what is called as the air geometry. And this particular air geometry is also a part created inside SOLIDWORKS. And they are assigned a material air. It's extremely easy to create the air geometry, and it is obligatory to create an air geometry to do an EM simulation using EMS. And the real reason is the magnetic flux is also existing in the air around the coil. And to be able to capture this magnetic flux, we need to be able to define the boundary inside which the magnetic flux will be present. And we need to discretize and mesh that boundary, and hence we need a geometry representing the air geometry. EMS uses a finite element type of simulation which first discretizes, or in finite element term, it meshes the air geometry and also all the other parts, and then it solves the Maxwell's equation to give you the results. So let me go ahead and just hide the air geometry, and then we can march forward with the rest of the problem definition. The next important step will be to define a coil. Now the definition of a coil is very simple. To define a coil, you need to specify the material or the parts that comprise the coil. Then we need to specify the cross-section phase through which strands of copper are wound or the current is passed. Then we specify the number of turns and the wire gauge of copper that is used to create the coil. Similarly, we can define the receiver coil as well, or the transmitter coil, where we select the coil, we select the cross-section phase as you see here. One can wish to show the preview to just see how the direction of the current will look like. And then we can define the number of turns and the wire gauge for copper that is used to wind the coil. Once the coil has been defined, we are now ready to go on to the next step, which is really to connect these things. And that's the real main topic for today, which is the circuit simulation inside EMS. Now, as you see here, circuit simulation can be carried out in multiple cases, and it's called circuit cases, where you can have different circuits for the same problem. The first step involved is to create windings. Now, basically, windings are nothing but coils or collection of coils that will be used in a circuit. So the first step would really be to drop the coils into their respective windings. So we have two windings, one winding which comprises the transmitter coil and the next winding that comprises the receiver coil. Once we have the windings done, we can now assemble them into a circuit using the circuit editor. The circuit editor that you see inside SOLIDWORKS is really simple to use. You have these circuit elements right here. We have both current source and the voltage source. We have capacitors, inductors, resistors, and a ground plane. One can just drag and drop things from the palette into the circuit to actually create a circuit as shown here. Once that is done, you can specify the value for the sources. So when you double click, you can actually specify. Let's assume that 1 volt RMS is the value of the voltage for the transmitter coil. We can also specify the value of capacitance and so on. And here is where the windings that we created, which comprised the transmitter and the receiver coil, are inserted into the circuit. Now we have two kinds of circuits, one in the transmitter coil, which just contains a capacitor and a voltage source, and the receiver coil contains the receiver winding, a capacitor, and a resistor or a load. Note that the inductance of these coils will be automatically computed by EMS and will be used during the simulation. So you don't have to manually enter the inductances. It will be done based on the geometry of your windings. Once you have the circuit, we are now ready to analyze the circuit and take a look at the results. In the interest of time for this particular demonstration, I've already pre-run the simulation, so we can go ahead and straight away look at the results. As far as the results are concerned, they're organized inside what is called as a result table. Now, inside the result table, one can read all the different types of results that one may be interested in. For example, we can compute the inductance, the self-inductance of the two coils, as well as the mutual inductance of the coil. One can also look at the flux linkages associated with both the coils. We can compute the coil resistances based on the geometry of the coil, the wire gauge used, and the number of turns, and so on. Next, we will look at the coupling coefficient. Notice here that we get a coupling coefficient of about 0.126 between the two coils. There are also other things that the result table of EMS will give you. Notably, the current. So we here see the current going through the receiver coil as well as the transmitter coil. So you can compute the real part and the imaginary part, and also you can compute the magnitude of the current that goes through the resistor, especially in the receiver coil. In addition to the current, one can also take a look at the induced voltage. This is the voltage induced in the receiver coil. So as a result, if you see here the result table that we obtained due to the simulation, gives you a lot of valuable information related to our wireless charging application. Next, we can also take a look at some of the qualitative results. For example, I can plot the magnetic flux density, a section plot of the magnetic flux density. You can see here through the coil as well as the aluminum plates and also the ferrite. Now I've hidden the air geometry. I can actually go ahead and show the air geometry and redo so you can see the section plot of the magnetic flux density including the air. So EMS is capable of giving both qualitative values such as section plot of the magnetic flux density, etc., as well as quantitative values such as inductance, induced voltage, currents, resistance, flux linkage, coupling coefficients, and so on. Now, let us move back to our presentation. And we went through a lot of these workflow. And basically it is, we have the model created in SOLIDWORKS. We can do a simulation in EMS and one can couple that simulation to a real life circuit where one can then run the simulation and visualize the results. So next, let us take a look at the product bundles and how EMS is bundled. Basically, EMWorks has two different products, main products. It's EMS and HFWorks for high frequency. For the purpose of this webinar, we will stick to the left-hand side or the EMS product. EMS has two basic bundles available, EMS electric and EMS magnetic. The example that I showed you using AC magnetic coupled to circuit, you need to have EMS magnetic bundle. Now, EMS magnetic bundle contains and can solve static problems, magnetostatic, AC problems using AC magnetic, which is a frequency domain type of solution. And we also have a transient magnetic, which is a time domain magnetic problem. Now, EMS bundles can be coupled to enable multiphysics. We have coupling to thermal, motion, structural, and circuits. And EMS license comes both as activation and network licenses. Now this is the basic product bundle. And to enable what you just saw, circuit simulation using AC magnetic, you need EMS magnetic bundle and you need coupling to circuits. Now here is a slide that talks about product-wise application for the EMS product. It ranges from low frequency all the way to high frequency. EMS can be used if you're designing electromechanical devices like motors, linear motors, solenoid actuators, loudspeakers, voice coil actuators, etc. EMS can also be used for wireless charging applications where one can study the performance of coils, the coil parameters, circuit parameters such as inductance, flux linkage, resistance, coupling coefficients, and so on. It can also be used in the field of electronics where one can study inductors, transformers, etc. And finally, our HFWorks product deals with passive RF and microwave components like couplers, filters, multiplexers, antennas, and it can also be used to conform to signal integrity type of problems. And these plethora of applications ranging from DC all the way to several gigahertz, they span across several key industries such as automotive, transportation, aerospace, consumer goods, energy, life sciences, and high-tech electronics. With this, we come to an end of this webinar. On behalf of EMWorks, I thank you all for attending today's webinar. You will be sent a recording to this particular webinar, so you are welcome to share that with your colleagues. You can visit us at www.emworks.com. Our website has multiple applications, application notes, and useful information that will enable you to understand the capabilities of the product. And we also have a EMWorks YouTube channel that contains hundreds of videos explaining the product under various applications. And you can also get access to our past webinars from our website. With this, I will open the floor to any questions you may have. So feel free to type into the chat window, and I'll take the next few minutes to answer them. Thank you. So I thank you everybody on behalf of EMWorks for attending today's webinar, and I hope to see you in a future webinar. Thank you and have a nice day.